Great. So welcome everybody. Good to see you all. And I hope everyone enjoyed doing the practicals last week. The things I saw were really awesome at the end of that. And those 3 weeks are now complete. So that kind of completes the block element of this module. And we're pretty close to complete on the teaching element as well of this module, at least in terms of the content. And then we'll have plenty of time for revision and discussion of what's going to come up in the exam, just so everyone's in a great position for that. So last week we finished off thermofluids and thermodynamics, and that kind of covers everything that's in the learning outcomes and on the syllabus for mechanical engineering. And the way that we've designed this module is all built around EPD really. And so the majority of what we talk about is mechanical engineering, because that's the stuff that people can really build into their EPD work all the way through their degrees. But we also know that EPD students will end up doing some electronics and some electrical engineering, and frequently some work with Arduinos or other small programmable devices. So today's class is an introduction to electrical engineering, really. And it covers, first of all, what kinds of things are in these small circuits that an EPD student might want to design with. And obviously, everyone in this group has already been working to power a motor. I saw people putting contacts to batteries in videos from last Friday and that kind of thing. So you know some of this already, but it will get a bit more into the, I guess, the lecture-based technical side of it rather than the applied side of it within this class. And then we'll also go into some of the calculations that we can do around circuit design. And in particular, the main thing that I think we want to take away today is that everything here is going to tie back to power. And we'll talk about electrical power and how we can understand how much power you're getting out of a battery. And then that helps you to tie anything you do in electronics into all the other ways of understanding energy and power that we've been talking through in the mechanical side of things. Because if you know that your battery is providing 4 watts and your motor efficiency is 50%, then that tells you that you've got 2 watts of power being delivered by your motor, and that might tell you something about the force you can drive something with, or the torque your motor provides, for example. So that's the kind of way that this, although it seems like this electronic stuff that we're going to do today is slightly standalone, I want to, every time there's an overlap with things that we've done before, I just want people to remember that in their own mind. Okay, let's make a start. We've got kind of 2 bits of the lecture today. The first is looking at some Arduino circuits and thinking about what they do and discussing them in a fairly applied way. And then the second bit of the lecture is writing down some equations that we can use to describe circuits. So let me share my screen. As always, I'll be keeping an eye on the chat, and so feel free to type anything in there. This is one of those classes where you can do a bit of guessing or working out what different circuits might do. So do, be ready to turn your mic on and have a go at explaining what's going on in each of the circuits we're looking at. At the moment, I won't ask people to explain this first circuit that's on the screen right now, but I want to use it just to kind of talk about the background here. We're going to sometimes look at like almost a cartoonish image like this one on the left of what the components we're dealing with look like. So we've got some batteries here, and I guess everyone recognizes what a AA battery might look like. we've got this board, which is called a breadboard, and it's a way of sort of testing circuits to see if they work. And then we've got some wires, one red wire, one black wire, and two small blue wires. This is called a resistor, and this is an LED, which is a light emitting diode. So I know everyone in the class will have different amounts of background in how much electronics they've done or how much they might have looked at things like this, but I hope everyone could make a guess. If there's a light emitting diode and a battery and not much else, this is a circuit that's going to light up the light emitting diode. It's going to turn on this red LED. And so that's the left hand side of the picture here is kind of a cartoon of it. And then we're often going to use these schematic representations, and each component is then shown in as a block on a block diagram. And that's a much easier way to understand what's going on in the circuit, because it tends to be easier to track what's connected to what. So, for example, on the right hand side here, we can see pretty quickly that the top of the battery is connected directly by a wire to the top of the resistor. The resistor is then connected directly to the LED, and the LED is connected back to the battery again. And that's slightly harder to see in the image on the left-hand side. Okay. So I'm just going to jump straight in with a list of the things that we need to know. And this is kind of the conceptual understanding of electrical engineering. If you've got a good sense of the things on this slide, you've got a good sense of how to analyze any circuit. But like all, it's a bit like Newton's laws. You can write it down quite quickly and you can memorize it reasonably quickly, but you can spend a lifetime working on the details of what it actually means. So first of all, a node is any point on a circuit. And I'm just going to go back here. So for example, we could say the top corner, well, all four corners of this image on the right hand side are nodes. And the net flow of electrical current, which is a capital I, and we'll come back to that, into a node must be 0. That means that the current that's flowing in from one direction must flow out in another direction. That's another way to think of it. And that already we're talking about a flow here. And so that is one way that some people find it helpful to think about electrical engineering, is like a hydraulic system with water flowing around it and driving certain parts of the system. And in this case, the flowing water, or the flow of the water, is the electrical current. I'm always a bit wary. It's one of those analogies that's kind of half useful, the flowing water as current analogy. But maybe if you keep it in mind and pull it out when you think it's useful and forget about it when you think it's not useful, then that's the best way to look at all of that stuff about flow and current. Between any two nodes, we can define a voltage. Ohm's law relates current and voltage across a resistor. So here's our first equation. This equation in blue is called Ohm's law, and it says the voltage is the current times the resistance. And again, we'll come and look at what that means. And then I said we were going to try and tie all of this back to power, because that's something we can relate to our mechanical engineering work. And so that's what this last equation does for us. Power is voltage times current. So I'll keep revisiting this slide just so that people can focus on the big ideas, I think. Okay, so let's take that way of thinking about things and apply it to a really pretty simple circuit. So we've got a battery or two batteries. An AA battery gives out has a voltage across it of 1.5 volts, and so two of them together gives you 3 volts. You don't particularly have to remember that, but that's just how this picture on the left corresponds to the picture on the right. And then we've got some wires and we've got a resistor. That's the kind of brown thing with 2 red stripes and a brown stripe on it. That's a resistor, and that resistor has a value of 220 ohms. And ohms, the Greek letter there is a capital Greek omega. So it may be worth remembering that. So what I'm going to do now, I'm just going to draw that circuit out, and then we will discuss what I'm doing. And let me put up the visualizer. Okay, cool. So this is that same circuit. One thing to note straight away, there are, as with all these things, there are different notations, different terminologies. The graphics that I'm showing in the PowerPoint come from a specific piece of software called Fritzing, and it's very good, but it's an American piece of software, and it uses a kind of squiggly line for a resistor. Historically, in the UK, we've used boxes like this for a resistor. So either one is okay as far as I'm concerned. Use whatever you're used to and comfortable with. I don't really think anyone will get confused by the fact that there are these two different symbols. And then we use these combinations of a long line and a short line to indicate a battery. But another thing that you can do, which is just as good again, is to just indicate that it's some kind of a voltage source. So I'll do that below. And so all I've done is a circle with a V in it indicates that I can write down the number of volts between a node just above that voltage source and a node just below that voltage source. And so one of the first big ideas we had was that a node is any point on a circuit. So I can say there's a node here and anywhere else I want to on the wires. But there's not a node. I suppose it's just helpful to note there's no node like in the middle of the resistor. It's the ends of things which are important in the circuit diagrams. And then also that wires don't really count for anything. They're just ways of connecting things up in this diagram. So the important things here are the voltage source and the resistor. And effectively what we're saying is this point at the top of the voltage source is directly connected to this point at the top of the resistor. Finally, one way to look at things again is you'll see people mark Earth onto their circuits sometimes, and you can do that. Ah, frozen. Has it unfrozen now?
And actually, for me, it just I get like a new frame every 10 seconds. So I listen to what you say, and then I see it 15 seconds later. So I'm actually okay.
Okay, that's not great, but you know, better that way than not getting the visuals at all. I'm sorry that the screen isn't updating as often as I'd like it to. The good news is I'm not really drawing anything very quickly, so you know, I hope it'll work out. And I'm afraid I think it's all a function of my bandwidth here in my house. So I'm not sure there's very much that I can do, but just keep shouting out. If it seems to have frozen for a long time, or if things are really unhelpful, just keep shouting out. Can you generally hear the audio okay?
Yeah, for me,
Yeah,
the audio
audio
is
is
fine. Mhm.
Cool. Harry, were you jumping in to say the audio was okay there as well?
Yeah, it's fine, it's fine.
Okay, great. So we'll keep going, but just keep noting things in the chat. Sorry, I'll be better at keeping looking at it, and then yeah, we'll be able to make it work. If necessary, I'll just stop doing as much drawing and we'll do things another way. So the important thing really is, I guess the important thing I've just added is an earth symbol at the bottom of the circuit. You can always define one point in your circuit, one node in your circuit as being at 0 volts. And so this is the symbol for earth, which is another way of talking about 0 volts. And then if that bottom part of the circuit is 0 volts and there's a 3-volt voltage supply, then I can make a note that this top node must be 3 volts. So we've got 0 volts down at the bottom and 3 volts up at the top, because they have to be separated by this 3-volt voltage supply. That's the kind of way we look at things. And that means if this point is 3 volts, remember I said that wires don't really do anything. So in fact, this point here is 3 volts and this point here is 0 volts at the top and the bottom of the resistor. And now I can write down Ohm's law, again from that list of the important points about electrical engineering, V equals IR. And I know that the voltage across the resistor is 3 volts, and that's going to be I multiplied by the resistance, which is 220 ohms. And I can rearrange that to say I equals 3 divided by 220. Which is 0.0136 amps approximately. We'll come back and just think about where I've got this capital A and amps from. But I can also, you can probably imagine from lots of the things that we've done in mechanical engineering, I can say that that equals 13.6 milliamps. So all I've done there is to multiply this number by 1,000 and divide the unit by 1,000 from amps to milliamps. So just going back, the units of current, we said current is a capital I and its units are amps, for which we use capital A. So V is voltage in volts, which also have the units V. I is current in amps, and amps have a capital A, and omega, which I'm never very good at drawing, I'm afraid, so feel free to make a better version of it based on the typed version on the slides. Omega is resistance. Sorry, R is resistance in ohms omega, which looks something like that. So I can box all of that off. So those are our definitions of the things that are turning up in Ohm's law. Why does any of this matter? Well, I guess one thing that matters here, just to finish off, there was another thing that we wrote on the list of important points, which was power is voltage times current. And now we know that the voltage across the resistor is 3 volts. And the current through the resistor is 13.6 milliamps. That's 13.6 times 10 to the minus 3. So the power is going to be 40.9 well, 0.0409 watts, and that's 40.9 milliwatts. So we've been able to do that kind of circuit analysis to work out how much power is going from the battery into the resistor. And so if this circuit is left connected up for a long time, the battery will lose energy because the battery is providing power to the circuit, and the resistor will dissipate energy. Dissipate just means lose, really. And what happens is the resistor here will get slightly hot, and then it'll heat up the air around it, and that's where the energy is going. So all of this fits in with our understanding from thermodynamics as well, that we're not gaining or losing any energy. The energy input is coming from the batteries, and the energy output is going to warming up the resistor and therefore warming up the air around the resistor. You might well say none of this is doing anything particularly useful. It's using a battery to heat up some air, and you would be entirely right. You know, this is the kind of circuit that it's very important to understand because it helps us to understand things that come later, but it's not in any way a practical circuit that we would want to use very often. Okay, let's go back to the slides. So I guess we've kind of now analyzed that circuit and that model. We've talked about some flows of current on the circuit. And I guess one thing left to say about flows of current, the flow into a node must be 0. So for example, if we define a node at the top of the resistor on the right hand side of the block diagram, then the flow of current in from above that node must be the same as the flow of current down into the resistor out of that node by the second bullet point, as it were, on those slides. And what that's really the better way to think of all of that, the way I've said it there is slightly confusing, but if there are no branches, the current just flows in around in the loop. So the current at all points in this circuit is the same, and it's that one we calculated. It's 13.6 milliamps. So just looking at some of the things that we're going to work with, the breadboard, I guess maybe it's worth just thinking quickly here. The breadboard is a piece of plastic with a whole load of holes in it for putting components and resistors and wires into, and then some of these holes that you see are connected up. So typically the vertical rows of 5 will all be connected to each other, and the horizontal rows just under the red lines and just above the black lines are also all connected to each other. And that turns out to be useful because you can make the red and the black lines the places where you connect up your battery, and then anywhere else you connect to those from, you know, you'll have either a +3 volts point or a 0 volts point, for example, if you've got a 3-volt battery. So this breadboard is just a useful way to put some electronics together, connect things up without having to, you know, if you don't have a breadboard, you might have to wrap wires around components and try and hope they hold together, or you might have to do some soldering, which is basically getting hot metal to hold two things together. You liquefy the metal, and then when it solidifies, it links components together. So the breadboard is for testing and moving things around in a simple way, and then later on you move to more complex ways of fixing your circuit together, because the breadboard has the disadvantage that it's very easy to pull components out. And at the very far end of things, you know, once you've really got an electronic circuit that you know is the right one, you can send it off to a company who will miniaturize it all and put it onto a printed circuit board for you. And then that makes everything much more amenable to being put into a product. And there's a piece of Autodesk software. I'm just going to put it in the chat now. It's called Eagle, and it's used for circuit design. And it's one of those ones where if you want to do some electronics projects right away, you might want to just start looking at Eagle now, and then it can take you through all the steps from a schematic diagram like we had on the last slide, all the way through to this idea of the printed circuit board and how things are going to be aligned on that printed circuit board to miniaturize it and everything else. And you'll know what a printed circuit board is. I'm just looking around me to see if there's anything I don't mind breaking open, but there's not. But I mean, historically, they've been small green flat boards about 1 or 2 millimeters thick, covered in components and with little sort of copper trails etched into the surface of them. That's a printed circuit board. Okay, so that's what a breadboard is. It's the testing version of a printed circuit board. Resistors in the breadboard kind of scale look like this, and they've got these stripes on them, and the stripes tell you how many ohms there are. And there's a system, it talks about here about a resistor color code table. You can look up for any set of stripes for any of these resistors, you can find out how many ohms they are. When you get to the level of a printed circuit board, resistors just look like tiny little black plastic dots almost, because they also get shrunk down. And then one of the things that we're now going to start talking about is an Arduino Uno. So these images come from the Arduino book. Let me just stop sharing my screen, and then I'll show you on the Moodle page. Well, let's do it on Aula actually. On Aula, under electrical engineering, you'll see the slides that we're going through now. And then you will also see this Arduino project book.pdf. And if you open up that Arduino project book, you'll see some of the things that we're about to talk about. So this is a Creative Commons open source book, and it's a really helpful way of understanding some simple circuits that actually do things and do useful things. And that's why we're using it here. So you'll see explanations of a number of the components we're going to talk about there. And that's on Aula or on Moodle, depending on which you prefer. Okay, so that's the Arduino is like the computer that runs all of this, because sometimes you want to be able to say, if the voltage at a certain point is more than 5 volts, then turn an LED on somewhere else or things like that. And so having a computer is very good for those if then kind of statements. And we'll look a bit at some of the functions that you might end up doing with an Arduino and how it works. But I guess for now, it's important just to recognize that a lot of the kinds of electronics that fit into an EPD course can be done quite effectively and neatly using an Arduino board like this. And then I guess you are now all experts or becoming experts in DC motors, because you've just been using them in your repeatable vehicles. And so a DC motor is one kind of motor, and that's what you want when you want things just to spin pretty fast. And often you'll have a DC motor combined with a gearbox or some gearing, so that you can trade off the speed for torque and keep the same power. So we'll come back and think again about DC motors, but I guess importantly now, we've gone from talking about resistors, which were pretty useless, to talking about motors, which are much more useful, but they all fit into circuits in very similar ways. A servo motor is a different kind of motor. Rather than just spinning and spinning and spinning, you control the position of it. So you use servo motors, like if you want to, on model aeroplanes, for example, you might want to control an aerofoil so it can just lift up through a range of about 30 degrees. That's an excellent task for a servo motor. So driving wheels that go on and on and on is a DC motor. Adjusting control of something with limited motion is often a servo motor, and there's also something called a stepper motor, which has a bit of both of those functions. It's kind of in between the two. Those are the kinds of motors we're likely to use in EPD projects. There are also things called AC motors. You can probably guess its direct current is DC. You power it with a battery. AC is like the mains, alternating current, but we won't do so much with AC motors. And in any case, you can they have different interiors to DC motors, but they do the same thing. You plug them in and they spin. So you can get exactly the same understanding from understanding DC motors. Okay, so now we've kind of looked a bit at circuits broadly. Now what we're going to do is look at some very specific circuits, and we're going to get into circuits that do something. So they don't just warm up a resistor anymore. They'll have a kind of increasing function over time. This one here, well, I guess let's open it up. What does this circuit do?
When clicked, it will light up.
Exactly. Yeah, great. So when you push the push button, which is this black circle with 4 pins attached to it in the diagram on the left-hand side, that means that the loop is completed, and so current can flow through the loop that's shown on the right hand side here, and crucially current will flow through the LED, and that will mean that the LED lights up. So that's how that circuit works. It's just worth noting some details on the left hand side. The Arduino has a whole load of things we can connect up to, and here the connections we're using are, one of them is called 5 volts and one of them is called ground. So we're using Arduino, our Arduino a bit like a battery there. We're getting some positive voltage of 5 volts and some 0 voltage or ground. And you can see that's in a section of the Arduino that's, it says power next to it. So the Arduino kind of tells you what each of these connections it's got is going to do. And then the Arduino itself is powered by either a USB connection or more complicated DC type thing like an old-fashioned phone charger, but that's fine. The important thing is, again, we've got some power from somewhere which we're going to need because the LED is going to light up, and that needs energy to do that. So there is, there is a circuit which does something, and in fact, which you can interact with because you can push the button. This one is then almost exactly the same, but it has 2 push buttons. So in both the cartoon and the block diagram, we've gone from 1 push button to 2 push buttons. And when I was talking about this circuit before, I said, okay, when the buttons are pushed, or when the single button is pushed, everything's connected up, and so current flows through the circuit. Now you can probably guess that we need to push both the buttons, for current to flow through the circuit. Otherwise, the 5-volt node up here is not connected in any way to the ground. So you always need to have a loop of some kind that connects up. So we call that what we had before, components in series. And, you know, sometimes we use this terminology anyway outside of electrical engineering. If things are in series, they're all in a line, and the current goes from one of them to the next and flows through them. And the alternative to series is parallel. And they're side by side like this, and the current can go through either of them. So now if we close either of these push buttons, if we push either of the buttons, there will be a completed loop. We can complete the loop either with the left-hand button or with the right-hand button on the block diagram. So that, I guess, is just a start to thinking about series versus parallel. If two things are in series, if two buttons are in series, they both need to be closed in order for current to flow. But if two buttons are in parallel, only one of them needs to be closed. And I guess this sentence in green maybe kind of summarizes that. In series, the current has to flow through each device. In parallel, the current can take different routes, so it can be divided. Okay, another circuit. Anyone want to guess or tell me what's happening in this circuit?
Do they light up in order or after certain times?
Exactly. Yeah, good. So, you know, you gave two possibilities here, and that's exactly right, because all of a sudden different things could happen with this circuit, because somehow things are being controlled by the pins number 3, 4, and 5 on the Arduino. So the LEDs are connected to ground, and they're also connected to pins on the Arduino, to 3, 4, and 5. And then there's still this push button around as well, which is connected to pin 2 on the Arduino. So all of a sudden we're using the computer, and exactly what we tell the computer to do isn't defined yet, but probably we're going to read in some information at pin 2. So look and see, ask the computer, has the push button been pressed? And then we're going to use that to control the LEDs. So maybe to turn them on when the push button is pressed. And one of the ways that we've kind of talked about electrical engineering in the coursework is by talking about sensors and actuators. So sensors are ways that you pull in information from the world, and actuators are ways that you do something to the world. An infrared sensor is obviously a sensor. It uses infrared to measure a distance, and then you can find out what that distance is. And a motor is an actuator because it spins in the real world, and you can use it to drive things in the real world. And here what we've got in this circuit already is some sensing and some actuating. The push button is a sensor. It tells you whether or not somebody is pushing the button. And the LEDs are actuators. They light up. So they do something in the real world. And I don't want anyone in this course to feel like they have to know how to program an Arduino at this stage. It's the kind of thing where the best way to learn it is to need to learn it, and then you do it quite possibly by reading this online book that I've shown you on Aula, and that's also available on Moodle. But I don't want that to be the focus of this lecture, but I do want everyone just to know what kinds of things happen in the program, what a program looks like, and what you'd have to learn if you wanted to start doing this Arduino programming. So the Arduino asks for two things. First of all, it asks for some information about the setup, and then it asks for some stuff which happens in a loop. And the setup happens once right at the start, and then the loop keeps happening forever until you stop it or turn the Arduino off. Let's look at that in some more detail. So this row 1 int switch state equals 0. For now, let's just forget about that. It's a part of the setup where we define things that we're going to want to talk about later on. But I'm less worried about that. What I want to look at is lines 2 to 7 here are the setup. So there was this void setup and then some curly brackets. Well, now we've put something into the curly brackets in lines 3 to 6. And what we're doing is defining whether different pins are an output or an input, whether we want that thing to be a sensor or an actuator. And so 3, 4, and 5, which connect to the LEDs, are outputs. Those are our actuators. And pin 2, which connects to the switch, is an input. We need the signal in to the computer, to the Arduino there, to tell us whether someone's pushed the switch or not. Then we do our loop, and I'll go through this reasonably quickly, but what we do is we find out what's happening on pin 2. So this digital read function gets information from pin 2, and it sets up switch state. So switch state tells us if the button has been pushed or not. And then I said earlier, computers are very good at these kind of if then or if else statements, and that's what we've got next. If we found out that the button is pushed, digital write different things to each of the 3 LEDs. Otherwise, else, digital write something else to the 3 LEDs. So there's one setup in lines 13 to 15, which is about what we do if the button's been pushed, and another setup in lines 18 to 20, which is about what we do if the button hasn't been pushed. So the sensors control the actuators. That's the key to the program, really. And then we do a couple of other little bits within the loop just to finish. We delay, so we slow everything down so things don't happen instantly, and we can do that in the program. And then we do something else with the LEDs to kind of say, okay, now we're moving on and testing the switch again. Delay again, and then it would go back and keep looping through from line 8 to line 27 over and over and over again. And that's roughly how programs work. We have some commands, we have some things like the if and else statements, and we tell our sensors and actuators what to do. Okay, let's move on. Another circuit. This one looks pretty similar in some ways to before. We've still got 3 LEDs, which we want to connect up somehow. But you can see in the block diagram, there's this new thing, which is a temperature sensor. And so, again, we can immediately divide up our thinking into sensors and actuators. The temperature sensor, it's right there in the name, it's a sensor, and the LEDs are a type of actuator. They do something, they turn on. And so we can start to make a guess about what the circuit's going to do. It's going to read some information from the temperature sensor, and based on that, it's going to do something with the actuators. So I would guess, looking at this circuit, the more the temperature sensor heats up, the warmer the temperature sensor gets, the more LEDs are going to turn on. That's the kind of thing that you could do. Again, we're not going to spend too long going through the code in detail, but it's the same kind of thing again. There's a setup in line 3 and a loop in line 10 or set up from line 3 to line 9 and a loop from line 10 to line 40. This time we've done something slightly different, which is in line 4 where it says open a serial port. We're assuming that the Arduino is connected up to a computer, and we're actually going to take some readings on the computer as well from that sensor. So that's something else we can do with sensors, as well as using them directly to control our actuators. We can record the data from them and then go back and look at it later. So you can use an Arduino to record data, and most of what's happening within the loop is calculating the temperature, doing some conversion from voltage to degrees based on what we know about the temperature sensor. And then the whole of the right hand side of this page is the same kind of stuff we saw before, changing what happens to the LEDs depending on certain conditions for the temperature. So you can see we've kind of built up one level of complexity from the last circuit to this circuit, and similarly we built up a level of complexity in the program. Again, I don't want anyone to memorize these programs or to feel like they have to be able to write them tomorrow, but it's important to know that this is all stuff you can learn quite quickly and you can be working with in your degrees. Does anyone want to guess what's going to happen here?
The motor should turn on when it's pressed now.
Yeah, exactly that. So there is a switch, and when that switch is pressed, the motor turns on. And I guess what's kind of neat here is you can see that pretty much just from knowing that there's a motor and seeing that there's a switch. You know, you can make inferences about these circuits based on some common sense, and I think that's often the key to it, without tracking through every wire and what's going on. And then when you look at this block diagram on the right hand side, you see that actually it's slightly confusing in a way. And the reason that it's confusing is because the motor isn't powered by the Arduino here. It's powered by this 9-volt battery. And what the Arduino does is control something called a MOSFET, which is like an electronic switch. And so the Arduino says switch the MOSFET on or off based on whether the push button is pushed on or off, and then that will turn the motor on or off. What I want people to have in mind here is, first of all, that this is a slightly more complicated circuit than for an Arduino, sorry, for an LED. And that's because motors sometimes take more power. And so we want to have their power supplies be separate, and then we need to control their power supplies. That's where the complexity comes in. But I think I saw on a lot of people's design challenge stuff on your coursework that you also realized you can make a motor spin just by getting a battery and 2 wires and connecting up the terminals of the motor directly to the battery. So this, in a way, is one level up from that idea. Rather than have the motor just spin and spin and spin and you have to physically unplug it to stop it spinning, you can tell the Arduino or any kind of microcomputer to switch the circuit on or off, and then that will connect up the battery indirectly, and your motor will spin or not. And if you want to go on and keep designing with DC motors from now on, you can start to take on circuits like this and build them into what you're doing, and then you'll have automatic control of when the motor's on and off. So there's some detail in the slides as well about the one component that I haven't talked about there is this diode, and it's really there so that the current through the motor only flows in one direction, and that's so that that's because motors are quite complicated. Every motor is also a generator. If you spin the motor by hand, you'll create a voltage across it, and then that spinning and voltage might do some damage to some bits of your circuit that you don't want. So again, we put in these bits of circuit design here involving a diode in order to avoid that. I don't want to get into what is a diode, how's it made out of, how's it made or anything like that. But I do want you just to know these are things you can look up. If you want a motor control circuit, you can look up what that motor control circuit should be. And I guess the reason I put the text on this slide is so that you know there is a reason for every part of the circuit, even if sometimes it's not immediately obvious what that reason is. The code here is pretty straightforward. It only runs to 16 lines, and really the key bit is it says if somebody's pushed the push button, then that will be recorded at pin 2, which is called switch pin. And we're reading from switch pin. So if the push button is pushed, tell the motor to spin. That's what this digital write motor pin high does. And if the push button isn't pushed, don't do that. Tell the motor not to spin.
So. Ben.
Yeah.
Do we get a Arduino board, or should we just purchase one ourselves?
Yeah. At the moment, we don't have a module in place where we're buying Arduino boards for you. But I it would be nice if we could find a space to do that. Certainly, if you needed one, say, for your final year project, you'd have a budget for that. And in fact, I think in DMP, Design Manufacture Project next year, there's budget to buy an Arduino there. So eventually, you'll probably find you might end up buying one within the budget of the course. But there's not one bought for you within this module at the moment. I guess while we're on that very practical question, the actual Arduinos are developed, I think, by an American company. They've got a large educational arm, and I can't remember exactly how much an Arduino is, but it's a few tens of pounds. And if you buy, there's a starter kit with a whole load of electronics. This book that this bit of the course is based on, and an Arduino. It's a nice kit, but it's something like 70 or 80 pounds, I think, to buy that whole kit. So, that's starting to get expensive for students, I feel. But if you win a prize and you win £100 anytime in the future, and you want to use that money to buy something related to your course, you could buy that nice Arduino starter kit. And then there is a Chinese knockoff company who available on Amazon and elsewhere and on eBay, and I think they're called Elegoo, and they sell fake Arduinos much cheaper. And I don't know where I stand on buying the original and expensive version versus buying the copied cheap version of things. But if you're on a budget, you may want to look into those alternatives. They all work just the same. So it's not it's not a matter of functionality in any way. And I think you can get a fake Arduino, an Elegoo, for something like £10. So that can be a good way to do it on a budget. But yeah, getting a cheap starter kit and having a play around will help you incredibly, just to know what this kind of stuff is like. So I do recommend it if you can, even though it's not within the scope of this module. Here we've still got a DC motor and a 9-volt battery. What do you think is different about this circuit from the last one functionally? What can we do here that we couldn't do before?
The rotations control the speed.
Exactly right. So there's this device in the middle of the cartoon, which is a potentiometer, which is well, another name for a potentiometer is a variable resistor, but it's something where we can change the resistance of it. And that means we can change the current that flows in some parts of the circuit, because we said resistance and current and voltage are all linked together. And using this, the black rectangle, 2/3 of the way down the cartoon breadboard, is called an H bridge, and it's a way of controlling a motor. Again, another level of control you can get over a motor. You can buy that chip, and then you'll find if you use the H bridge and the potentiometer, like in this circuit here, then you can start to control the motor's speed. And I guess everyone can now see from all the coursework you've been doing why it's going to be useful sometimes to control the motor speed electronically. The alternative is you just always run the motor at full speed and you use some kind of mechanical system like gearing to control the output speed from it. And sometimes you want to control the speed electronically, and sometimes you want to control the speed mechanically. So you can see the configuration of what connects up to what is now getting slightly tricky, and this breadboard is getting slightly messy. It's got crossing wires all over it, and one of the skills, again, that you just pick up if you work on these kind of electronics projects a lot, is keeping your boards nice and tidy, and being able to have something where it's always reasonably easy to work out what's connected to what. So in general, these fritzing diagrams should be fairly tidy and clear about what's connected up where. And you can see now we're into a longer program. We're up to 53 lines of program, but it's still got many of the same things that were going on before. We're doing this kind of digital write, which is how we've always controlled our actuators, and somewhere down in line 23 and 25, there is digital read, which is how we've always taken information from our sensors. So although the complexity builds up, the process remains quite similar. We read information from sensors, we do some calculations in the computer, and then we use the outputs of those calculations to control our actuators and to do something out in the world. Okay, that is the first part of this lecture complete. I will stop sharing. And so what we've done so far is really to, I hope, give a sense of why electrical engineering is going to be important in EPD. And I think really one of the main things to take away from that is this idea of sensors, control system, and actuators. Things that read information from the world, things that manipulate that information, and then things that act on that information. Are there any questions at the moment? Okay, in that case, what I think I'd like to do is take a 5-minute break for everybody. And you can stretch your legs and go and get a cup of tea. And then we'll start again at 15:08 on my computer. And we'll be going through some more of the kind of maths of the circuit block diagrams and trying to relate those voltages, currents, and resistances, because that's the other real key in electrical engineering. So I'll see you back here in 5 minutes and then we'll get started again. Okay, that's 5 minutes. Let's go again. I will share my screen. So this is now the other side of things. As I say, this is about calculating voltages and currents. This is the same kind of first circuit that I talked about last time around, with an LED and a resistor and a set of batteries. So we know now that the resistor will warm up slightly and the LED will light up and warm up. But just to kind of give some context, one thing that's going to happen here, the LED always has about 0.7 volts across it. And so if there's 3 volts from the battery, 0.7 volts across the LED, then we would calculate there are 2.3 volts. The remainder of the voltage is across the resistor. So we know 2.3 volts across the resistor and 220 ohms means we can calculate the current through the resistor, and then that in turn will be the current around the whole loop. So we can find the current in the circuit. Sorry, I'm just going to drink some water. So that's the, I mean, obviously when I say that out loud, it's much less clear, and we'll do some writing things out in this lecture. But you can see the kinds of things that we might end up doing, using voltages to calculate currents, using currents to calculate voltages, and then somehow combining all of that and going back to thinking about power again in the end. So just to reiterate the big ideas from the last lecture, we defined what a node is. It's a point on the circuit. Current into a node must be 0 in total. So that means whatever flows in has to flow out of a node. And between any two nodes, between any 2 points on the circuit, we can define a voltage. So a voltage is between 2 points and a current is through something. That's an important distinction to have in your mind, that they are they're talking about different things in a way, a voltage and a current. They don't overlap, but we can link them using Ohm's law for a resistor. Voltage is current times resistance, and we started looking at that in the last lecture. And then power is voltage times current. And this is the circuit that we actually worked out in the last lecture, and we got as far as finding the power that's dissipated in this resistor. Okay, so here's a circuit that is one step more complicated. I'm going to put the visualizer back on. Again, I'm sorry if it's a bit choppy in the feed, but I hope you'll be able to at least get still images which show you what I'm talking about as I go through. So I think from memory, in the diagram that was shown just there, it looked something like this. And maybe this was 3 volts, and this said 1K, and this said 1K. And you'll see very often 1K used, which as 1000 ohms, so 1 kilo ohm. And that's exactly the same kind of notation, SI notation, as we've been using a lot. One thing that you can do that I want people to get into the habit of pretty quickly is you can just redraw the circuit, moving the wires around however you want to. And I sometimes find it easier to draw the circuit like this. It's exactly the same circuit that I've drawn in green. I've just moved the wires. I stretched out the wire that goes from the battery to the first 1K resistor, and then I turn that resistor around 90 degrees. And now everything is at least down one side of the all the resistors are aligned down one side of the circuit diagram, which helps me a bit. Now I need to try and answer something about the same kind of thing we did before. What's happening here in terms of currents? We know something about a voltage. We know something about resistance. And we need to try and calculate something about current, and then we'll have analyzed the circuit as far as we want to go. I'm going to also just do the same thing that I did before of marking some point as being at ground or 0 volts, and that means this point here is at 3 volts. And then we can do a few things. You know, we could look at this and say, okay, by symmetry, in between these two resistors, half the volt, they're the same resistance. So half the voltage is likely to go across the top resistor and half the voltage is likely to go across the bottom resistor. And so we can mark on probably in the middle of them will be 1.5 volts. But all I'm going to do instead is make a note of something. Resistors in series add up. So I can say that in some sense that diagram I've just drawn is equivalent to this one. With a single resistor, which is 2K. And I guess, you know, most people might well have intuited that anyway, have kind of had a sense that these two resistors right next to each other could be combined into one resistor with their values added together. And that intuition turns out to be right. Now we can treat this in the same way that we treated a very similar looking circuit before. I'll go a bit quicker this time. V equals IR, which means rearranging that equation, I equals V over R, which equals 3 volts over 2K, 2000 ohms, which is 1.5 times 10 to the minus 3 amps, alternatively 1.5 milliamps. And now one thing that can be helpful, I've used these 3 lines here. More often they're used horizontally, but they're kind of used to say 2 things are equivalent. So what I'm saying is this circuit is largely equivalent to this circuit. And that means if the current flowing all the way around this circuit is 1.5 milliamps, the current flowing all the way around this circuit is 1.5 milliamps, and I can mark that on my diagram there. So one of the techniques that we're going to use in electrical engineering is to keep redrawing circuits, simplifying bits or rearranging bits. And then we'll go back sometimes to our earlier drawings, take something we learned from a simplification and put it back into the more complex model. And that's a very standard way of kind of working through these electrical engineering type problems. Now that I know the current here, I can do a final thing, which is to calculate a voltage. For example, if I want to calculate the voltage between these 2 points, I'll call it V1. Then we know V1 equals IR, which is 1.5 milliamps multiplied by 1000 ohms, and that's going to come out to be 1.5 volts. And that's kind of what we guessed anyway. that in between the two resistors, because of some kind of symmetry, there would be 1.5 volts. Each of them kind of takes half of the 3 volt supply. So that's circuit analysis. That's the kind of thing that we're going to do in this lecture. And I guess what I haven't done there is to work out the power dissipated in each of the resistors. I'll leave that as an exercise for you, knowing that power is voltage times current. I think we've got all the bits ready to go to work out that power. This rule is what I wrote down on the paper there as well, on the visualizer. That if resistors are in series, you can just add up the resistances to get the overall effect. So that these two 1 kilo ohm resistors in series have the same effect as a single 2 kilo ohm resistance would. Now we need to think about what happens if we have two resistors in parallel. And again, this slide kind of gives the game away. It says the same voltage will apply across each path. Along a wire, the voltage is the same at all points. It only changes across a component. So the voltage just above, where I might mark on 3 volts just above the battery, is the same as the voltage just above R1, and it's the same as the voltage just above R2. So let's take a look on the visualizer at what that means in practice. The circuit looked something like this. Like so. I'm going to mark on that I define the bottom of the circuit as being earth or ground, and so it's at 0 volts. And so I can say, okay, this point here is at 3 volts, and in fact, anywhere that's connected by a wire to 3 volts must be at 3 volts. So all those points that I've kind of done the dotted lines from now are going to be at 3 volts, and anywhere that's connected by a wire to 0 volts must also be at 0 volts. So that's kind of good because now we know the voltage across these resistors. We can work out some currents, and I'm going to mark those on as I1 and I2. I1 is the voltage across the resistor divided by its resistance, which is 3 volts divided by 1K, which is 0.003 amps, 3 milliamps. And I2 is going to be exactly the same because it's also 3 volts and it's also 1K. Now, there's one other thing that I can use from that list of big ideas that we drew out earlier, just to finish analyzing this circuit. If we look at this node here, it's got 3 paths in or out of it. I1 and I2 are both flowing into it, and then I've marked on I3, which is flowing out of it. And we said that the total current into a node must sum to 0. So I1 plus I2, the currents flowing into the node, must equal I3, the current flowing out of the node. I1 plus I2 equals I3, and therefore I3 is going to be 6 milliamps. So in this circuit, going back, in all of our previous series circuits where components were in series, we had the same current all the way around. When we have components in parallel, there are branches. If you think about current flowing along the top of the circuit, then when it reaches the top of the first resistor, it can choose to go left or right. And some current goes left and some current goes right. And we have the tools now to calculate how much goes each way. But that means the current at different points in the circuit will be different. So if you have branches in the circuit, you'll have different currents within the circuit. Okay, back to the slides. This is the same kind of thing that we've done on 2 slides ago. It's a series circuit, so everything is in one loop and there are no branches. But this time we've got different resistances. And I guess what we're always trying to find is what's the total current and what's the voltage at each node, at each point in the circuit. Those are the kinds of things we might be interested in. So I'm just going to copy out this diagram. You might want to do the same just now and start thinking about how you would analyze it. I'll put the visualizer on. So I've copied out that circuit. One thing that you'll notice I do as a shorthand when I'm just drawing out circuits for analysis, technically this is actually should be 1 kilo ohm and 1.5 kilo ohms like that. But I'm not too, it's a convention that sometimes you just write down 1.5K. So, you know, you'll notice me occasionally doing that, and don't worry too much about it while I'm using these circuits for analysis. But I think I should, you know, if the question is, what is the value of this resistor, then I should finish up definitely by writing it out fully as K ohms. Okay, what we did before was we combined all of the resistors. We said resistors in series add up, so we can combine them all. This is 1000 plus 330 plus 1500, and that, if I write it all out as one resistor, is going to be 2880 ohms. And now we know the voltage, we know the resistance, and so we can say, okay, V equals IR, therefore I, the current, is voltage divided by resistance, is going to be 3 divided by 2880. Sorry, I've done that addition wrongly in my head. It's 2830. And that comes out as 1.06 milliamps, 1.606 times 10 to the minus 3 amps. And then I can say, okay, well, if this is 0 volts, then this point here is going to be 0 plus IR, the voltage across this resistor. So it's 0 plus 1500 times 1.06 times 10 to the minus 3. And that equals 1.59 volts. And then I can keep on going. I'll change color to green just so it's clear where I'm looking at. This is going to be 1.59 plus 330 times 1.06 times 10 to the minus 3. And that's 1.94 volts. And then we know that this point here, because it's connected by a wire to the top of the voltage source, is going to be at 3 volts. So we can work out the voltages all around the circuit. We know the voltage across each individual component, and we can work out power dissipated in each individual component. Again, this is done for being able to analyze the circuit. You might say it's a bit artificial to do all of this with resistors. Why do we care? But of course, these might become later on motors or lights or all kinds of things that are important. And you need to know how much power you're putting into each of them by your circuit design. Let's keep going. We can do the same thing now, but rather than using numbers, we can use algebraic terms. So we don't know anymore what the voltage is or what each of the resistances are, but we can see where we can get to anyway. So let's try that on the visualizer. And again, while I'm drawing this out, please do think about drawing it out yourself and see how you get on. I'm going to call the voltage just V, and then we had R1, R2, and R3. So I can say, okay, RT, the total voltage is, sorry, the total resistance is R1 plus R2 plus R3. V equals IR. We know, I guess maybe actually it's easiest if I redraw the circuit again so that I'm following exactly the same kind of pattern. We know on this right-hand circuit that I've just drawn out, I is going to be V over R T, which equals V over R1 plus R2 plus R3. And so if I now want to know the voltage here, Vx, let's say, then I can do the same calculation that I did with numbers before, but now algebraically with letters. I can say, okay, V equals IR. Vx must be 0, the voltage here, plus the voltage across R3. Which equals I multiplied by R3, which equals V times R3 over R1 plus R2 plus R3. And if you want, you can put the numbers from the previous question into this algebraic formula, and you'll find out that they come out the same. If you make R3 1.5 kiloohms, R1 1 kiloohm, and R2 330 ohms, and V 3 volts, you'll get the voltage here at X is 1.59 volts, just the same as we got in the last question. So sometimes it's easiest to work in numbers. Often in engineering, it's good to keep things in terms of the algebra, because now we've got a formula that we can keep on reusing over and over and over again. And in some ways, we've got a clearer understanding of what's contributing to the numbers we're getting out. you can get the analysis coming at you in different ways as well. In the last few circuits, we've been trying to work out what all of these voltages are at different points in the circuit based on the resistor values. In this question, we're given the voltages, so we don't have to calculate those, and we're given a current, but we don't know all of the resistor values. So we find out the voltage across each component, like the voltage across R2 must be 12 volts, just from where we've defined 0 on the circuit and where we've defined plus 12. And if we know the voltage and we know the current, we can go on and calculate the resistance. So I'm not going to do this example that's on the screen right now. There are worked examples available for everything, of course, on Moodle and Aula. But I recommend just taking a look at some of these examples and seeing how you get on with them. This is the next one that I wanted to get to and go through. I think we've really got a good grip now of series circuits and how to analyze them. And then we need to come to a parallel circuit and think about how to analyze this one. So here, the parallel circuit, the voltage across each of these resistors is going to be the same, because the voltage all the way along the bottom is ground if we define that as being 0 volts, and the voltage all the way along the top is plus 3 volts. So let's draw that out and again see where we get to with some analysis of that. I'll bring up the visualizer. Sorry, I've forgotten the values already. 220, 100 and 150 ohms. Okay. So I marked that up on my diagram. And I guess what we might want to know is some currents. So I'm going to mark I1, I2 and I3 on my diagram. And again, for each branch of the diagram, we now know something fairly straightforward because we know the voltage and the resistance. So from V equals IR, we can write down I1 equals V over R1, which is 3 over 220, which is 13.6 milliamps. I2 equals V over R2 is going to be 3 over 100, which is going to be 30 milliamps. And finally, I3 is V over R3 is 3 over 150, and that is going to be 20 milliamps. And then I guess one last thing that we can do is to mark on here IT, I guess I total, and we can say, okay, IT, it's this same thing about the nodes. The current that flows in IT must be all of I1 plus I2 plus I3. We can't lose any current, so they all have to add up together, and that comes out at 63.6 milliamps. And now we can do one last kind of useful or clever thing, which is to say, okay, now imagine we've got another circuit with a 3-volt supply. And there's just one resistor, which is kind of the equivalent resistance. and we're going to get 63.6 milliamps as the current in the circuit. Well, in that case, R equals V over I, which in this case equals 3 over 63.6 times 10 to the minus 3. Which is 47.2 ohms. Why does that matter? Well, I guess what we're saying is that this, if you draw a circle around all of those resistors together, if you wanted to replace everything in that circle with one resistor, it would be a 47.2 ohm resistor. And that's kind of interesting already, because that's a smaller number than all of the individual resistances. We had a 220, a 100 and a 150, and together they have the same effect as something that's like 47.2. So resistors in series in some of the previous examples added up, but these resistors in parallel don't add up at all. We end up with a smaller output than any of the individual resistances. That's a key thing to kind of hang on to. And you could probably guess, just like in the series examples, we went from looking at things numerically in terms of numbers to looking at things algebraically. We're going to want to do the same now with the parallel example. This, I will say, is kind of the last big example of today. If you can sort of keep a handle on everything that we've done up till this slide and then this slide, everything after this is kind of more than it goes beyond the scope of the course. It's kind of exploratory, and it doesn't really actually get much more complicated. This is about as complicated as we want the understanding to be. So one last time, I'm going to write out the diagram. One thing that I hope you'll notice is that I've already, just within this lecture, drawn out about 20 circuit diagrams, and that's the nature of electrical engineering. You end up drawing circuit diagrams a lot, and you're all people who think onto paper a lot anyway, and that's a real benefit here. Being able to keep redrawing diagrams, keep drawing them from in slightly different structures is all very helpful. And sometimes people who are much less visual get stuck because they don't redraw often enough. So be ready to redraw your circuits an awful lot. Okay, I'm going to mark on the same kinds of things that were on my previous diagram when we had some numbers, but now we don't have any numbers anymore. But that's really all right. I'll also mark on that we've got ground at the bottom of the picture. So what we do is for the same process that we followed before. I1 equals the current in this branch is the voltage across R1 divided by R1. So it's just V divided by R1. I2 equals the voltage across R2 divided by R2, V divided by R2. IT, again, it's the same kind of analysis that we were doing with numbers before. It's just the sum of the currents into this node. So it's I1 plus I2, which equals V over R1 plus V over R2. And I'm just going to rewrite that using some brackets. It's V multiplied by 1 over R1 plus 1 over R2. now I can do one bit of slightly tricky algebra. You know, this in a way is an answer. We wanted to know what the current was, and we've got it. But if you remember in the last example, what we were able to do was to replace everything with a similar circuit with a single resistor and call this RT. And this is V, and this is IT. So we can say, OK, RT equals V over IT, which equals V over V 1 over R1 plus 1 over R2. It's V over IT is V over this. We've just calculated IT and I've written it into my new equation. The V's will cancel out, and so it's 1 over R1 plus 1 over R2. And then this is the kind of tricky fractions within fractions type thing that I think you've covered in maths, but is always slightly hard to remember what to do with, I think. But what we can do is multiply top and bottom of this fraction by R1, R2. So this then equals R1, R2 divided by R1, R2 over R1 plus R1, R2 over R2, which equals R1, R2 over R1 plus R2 when we rearrange it all. So resistors in series were quite straightforward. RT, the total resistance, we just add them all up. Resistors in parallel are a bit tricky. This is something that it's not that straightforward to remember. So I guess remembering this kind of analysis helps you to get to how to deal with resistors in parallel. And the more you work with these problems, the more that kind of thing will be memorable to you. Okay, like I say, that's really where I want to get to today, but I just want to take 5 minutes more to look at ways we could expand this out. So that's the result that we've just calculated. It's there in the slides, and you'll see this, the two vertical lines mean in parallel. So that's a notation that sometimes we use. And that the total resistance of two resistors in parallel is this slightly fiddly algebraic expression, which is a fraction. You can imagine that we could expand this out to 3, 4, 5 resistors in parallel. And there, the easiest way to remember what to do is to look at this here. 1 over RT is 1 over R1 plus 1 over R2. If you look at it from a different angle, I can just make a note of that. 1 over RT here equals 1 over R1 plus 1 over R2. That's taking this expression in blue, the two ends of the expression in blue, and flipping both of them over, so inverting both of them. Then when we come to look at something similar with 3 resistors, we can make a good guess about what the total resistance is going to do. Instead of being 1 over R1 plus 1 over R2, it's now 1 over R1 plus 1 over R2 plus 1 over R3. So this is something where we can scale it out to lots and lots of resistors in parallel. And then we start to get into circuits where we've got things in parallel and things in series all at the same time. And now what we might do is, first of all, well, I'll just draw one more thing, which I think I can do without, I won't go through the calculation, but I can at least show you the kind of drawing that we might end up doing. The circuit looked like this. And this is one of those places, sorry, connect that up, where it's really helpful to do the this circuit is equivalent to that circuit kind of trick. We'll just leave the series resistor that we had, and then we'll take these two parallel resistors and combine them together. And this new resistance is RT, and we know how to calculate that. And now we've got a circuit which is a series circuit and is relatively straightforward to manage and work with. So that's the kind of process that we would go through with these more complicated circuits, trying to reduce them to being a purely series or purely parallel circuit where they're easier to work with. This example, you know, if you want to go away and test yourself after class to see if you've really got the hang of things, this is a good one. I guess the way that I would describe it is R3 and R4 are in series. They line up next to each other, in a line with each other, so you can combine them. Then R2 and that combined R3 and R4 will be in parallel, and so you can combine them, and then you're left with a series circuit, and you know R1 and the combined effect of R2, R3 and R4. And then the last two slides that I want to talk about, and then we'll stop, are just to let you know the kind of formalization of all of this, of everything that we've been talking about, are two different historic electrical circuit analyses done by Kirchhoff. So there's Kirchhoff's voltage law, which says if you add up all the voltages around a circle, they have to add up to 0. So the 3 volts from our battery in our first example had to correspond to 3 volts in our resistor in order that everything adds up to 0. And that we've kind of been using that throughout, but without having formally written down what we mean. And then Kirchhoff's current law, again, we've kind of been using this throughout, saying that the current that goes into a node must equal the current that comes out of a node. And we had that right from the start. And that helps us, again, to formalize this as a law. And then you can start to do, I'm just going to jump here, for example. This is a bit like some of the circuits we've already had a quick look at. But instead of redrawing the circuit, another way to do it is to start writing down equations based on Kirchhoff's voltage law and Kirchhoff's current law. Because design students are usually so visual, I think the redrawing the circuit approach and reanalyzing by redrawing is the best one for us and for this class. But if you're somebody who just really likes equations, then you can do everything using equations only from Kirchhoff's voltage law and Kirchhoff's current law. And that's, I mean, I've added in more and more examples getting more and more complicated. You can see this kind of thing with like 3 parallel branches, but slightly confusing where how they line up is really getting quite hard to analyze. Yeah, I guess that one's more straightforward to analyze, except that this time, instead of having a voltage supply, we've got a current supply, which again is something that you can arrange if that's what you need to design your circuit. So let me stop sharing and close out in 2 minutes. The really important thing here is that all of this has a very practical set of applications. And that's really what I've tried to bring together today for the electrical engineering is the sense that this all adds up to a way to run a motor, or a way to turn on a light, or a way to find the reading on a temperature sensor. but just having those basic ideas about circuits with voltage supplies and resistors really makes you familiar with the ideas of voltage and current, and those tell you things about how fast your motor is going to turn or how bright your light is going to be. So the second half of the lecture is a way of getting the mathematical understanding that informs how things are actually going to work in the stuff from the first half of the lecture. And that's really the substance of today. Any questions on any of that electrical analysis? Okay, good. In that case, the last thing that I want to say is, obviously now we've completed the lecture content, and I don't think we've got a lecture next week. So our next time we all meet up will be after Easter. And I know we've got 3 hours worth of lecture time, that 2 hours from when I changed job in October last year, an hour from earlier in this semester, that I want to catch up on. And one thing that I'm leaning towards is arranging a face-to-face revision session for this class, but I know that might not work for everyone, so I'd have to have some way of doing a video link at the same time. But I just think being able to all meet up would be nice. If we can do that after Easter. So I'll look into the possibilities there and of having a video link at the same time. Your exam, I think is in May, and that will be an online exam. And really now what we're doing is just getting everything in place for the exam. And then everyone should be in a good position to do really well in the module and go flying on through to next year. So that's what we've got left in this class. Okay, I'm going to stop the recording, and then things are done for today.